They may call me anytime in between. Okay, if that is the case, I will just drop everything and go off.
Okay, sir.
Okay. Yeah. I don't know if it happens now. I will leave. Just bear with me this time. In that case, the presentation may have to be repeated next time. Whatever.
No problem.
Okay. So first, who's presenting in group 9?
Yes, sir. I am presenting, sir. Raj.
You have negotiated with Shyamla?
Yes, sir.
Shyamla, is it okay?
Yes, sir. It's okay, sir.
Yeah, okay. So, what's your roll number? Raj?
55.
Hmm?
55.
55. Okay.
Yes, sir. Can I start sharing my screen, sir?
Just hold on. I'll tell you. You can start sharing screen. I'll tell you after I start, you give the presentation. You share the screen now. No problem.
Okay, sir.
Yeah, you can start.
Is the screen visible?
Yeah.
Okay. So, good morning, everyone. I'm Raj, and today we are going to present on the second activity that was given for this week, that is wing loading selection. And our aircraft specification is regional short haul aircraft. So, in this, we would be studying about how wing loading selection could affect various other parameters. So, let's get started. Basically, wing loading is, as we all know, is just the ratio of gross weight of aircraft to the platform area. So,
கூப்பிட்டாங்க சொல்லுங்க. You continue. I was talking here.
yes, yes. So, wing loading is defined as the ratio of gross weight of aircraft to the platform area, and it affects various other parameters during the mission profile. So, these are some parameters to also
Yeah.
noted.
First of all, show all the specifications of your aircraft.
Specifications of the aircraft, sir.
That should be the first slide in all presentations. That is what I specify and what you added, and what you got from FAR.
Sir, actually, we haven't written it as such, but it's written in the slides, sir. I'll make a slide separately for that also, sir.
No. In your report, you have to include, but every slide you make,
Okay.
you include all these three in all the presentations for all groups.
Okay, sir, for sure.
Okay. So, can you just briefly tell your, these three to me now? Can you orally tell? That's okay.
The specifications, sir. Sir, like the total takeoff weight that we estimated from.
No, not this. I would have given you, short haul means what is the range, what is the endurance. Will they
Yes,
give anything like that? Yeah.
we were specified with the range, sir.
Payload, yeah.
Not much information regarding that, but the range is 250 kilometers.
Cruise speed.
Cruise speed, we assumed cruise Mach to be 0.4. It wasn't.
It's not given. No. I told you. Have I given you that?
No, sir. It wasn't given.
Yes, sir.
Yeah.
From the survey, you had asked us to take the turboprop values.
No. That is okay, but that is something you got from your whatever I have given initially. That's what I want. That is only the range, 250 kilometers only.
Yes,
sir. You gave us the range and cruise speed specification.
You gave us the time period, so we have to. It should be 1 hour,
speed.
1 to 2 hours
That is
starting takeoff and
so
landing.
what is that means I gave you a speed specification.
Yes, sir.
Cruise speed
Yes,
indirectly. Yes.
Yes, sir.
And then I also given you the. Did I give you airports or not?
Yes, sir.
You give, sir, from Huntsville to
Atlanta to Huntsville.
Yes.
Let Raj answer this time because
Yes,
he's
sir.
getting most of the marks. Yeah, it's okay. You can chip in, but only if Raj is unable to answer, you can help him.
Yes, sir. So,
Yeah, Raj,
so
what I want is well, that's all is given.
yes, sir.
Okay. Yeah. Then passengers, number of passengers.
Around 50.
So that is your payload.
Yes,
Payload as
sir.
specified indirectly.
Payload. Yes, sir. Payload. So these were the specifications, and we'll be discussing about the effects that wing loading has on various parameters.
What about yeah, landing, climb? Let's see.
Yes, yes, sir. So
Mhm.
this was the mission profile of our aircraft that has to take off from Atlanta and land at Huntsville.
Hmm.
So the first step would be the determination for the platform area.
Hmm.
So using this table, and our aircraft falls in the short medium range, we have assumed um, the W by S ratio to be 95 from the table, and from the activity one, we got the total takeoff weight to be 18,534 kg.
No, this is not the way to do. See, the first group to present will always have this problem. Okay. So I appreciate your efforts, but this is not the way to do this exercise. You don't estimate wing loading through this. This is given for you as just a reference. You have to find the wing loading for your own aircraft because I want you to go through that exercise. That is the whole point. You take it from this, you don't do anything there.
So we had to take it from the literature data, sir.
No. What do you want to do now? First step, what are you doing? Take off length. Huh?
Yes, sir, takeoff.
Take off length. Okay. So let me share the something with you again.
Okay, sir.
So tell me what you have done for takeoff. Let's start with that, then we go to what
Yes,
else.
sir, sure. So we have calculated the platform area,
Hmm.
and using the platform area, we would get the takeoff parameter and takeoff distance, and for various takeoff for various takeoff distances, we would plot the graph and analyze where our wing loading should fall for the correct that T by W
Hmm.
versus W by S.
Okay, that plotting is okay, but I'll tell you what to do. Hmm?
Okay, okay, sir.
Now, I mean, many ways of doing design, but this is what I want you to do. Okay,
Okay. Yes.
so let me put it like that. Rather than calling what you have done is wrong, I'll tell you that what you have done is not according to what I want. That's all.
Okay, sir.
Right. So wing loading. If you go through the book, okay, 3.1, hmm,
Okay.
section 3.1 is a takeoff. Okay.
Yes, sir.
Now, first you estimate the takeoff velocity. For that, you can go to the reference aircraft. Roughly, it will estimate, that takeoff velocity.
Yes, sir.
You may need this takeoff velocity later. Okay.
Okay.
Right now, you try to plot. You go to figure 3.2. I can just show you that figure there. Hold on. Shall I share the screen
Yes.
temporarily?
Yes, sir. Sure, sir.
Okay. Are you able to see my screen? Not yet. Huh?
Not yet, sir.
Not yet, sir.
Actually, I didn't actually share. Okay. Figure 3.2. You remember this figure?
Yes, sir.
Mm. Now, what you do is this shows CL max and X axis is taken off on Y axis. Okay. Instead, I want you to plot the same thing. Wing loading on x-axis and T by W on y-axis. Okay.
Okay,
So
sir.
what I want you to plot is this, right? X-axis we have wing loading. Okay. On y-axis we have T by W. Then you look at, sorry, on this one. Equation 3.3 and 3.5. Are you able to see?
Yes, sir.
What does equation 3.3 contains? WAS takeoff 1 by CL max. You assume a suitable CL max. There you can go to references or consult the table. You are free to do that. Okay.
Okay, sir.
Choose a suitable CL max. Then you see this relation as wing loading. Okay. TOP as wing loading. W by T is nothing but T by W, the whole inverse.
Yes, sir.
Correct? This is takeoff parameter. Now substitute this expression in 3.5. Okay.
So we'll get equation in terms of W by S and T by W.
Yeah. Here inside the root they will cancel. W by T and T by W will cancel each other.
Yes, sir.
But outside you will have the W by T still there.
Yes, sir.
Right. So now this S takeoff is indirectly given to you in your specification. You have the airports, right?
Airport line.
So you take the length of the airport as constraint. If it's short haul, probably it will have excess of. In Huntsville is the great problem here. Huntsville may have a smaller airport, but Atlanta may have a very large airport. So your constraint will be Huntsville.
Okay.
Take that airport's sea level. I mean, how much height is sigma you take from that height for Huntsville,
Okay.
or even both airport. Then STO takeoff length you get from the aircraft runway length. Assume it's 60 to 70% of that length is the takeoff length. You get suppose runway length is 100 meters. Your takeoff length should be only 60 to 70 meters. Got it?
Yes, I got it, sir.
Yeah, because in case of engine failure, you need some buffer distance to
Yes.
come to a stop. So
Okay. Okay, sir.
take that as STO.
Sure, sir.
You will get some graph like this. Okay. Okay, STO is, I'm telling 300 meter. Make sure both these are an appropriate unit. TBW is just a ratio. Wing loading, it should be in, if it is in Newton per meter squared, STO should be in meter. If wing loading is pound per feet squared, STO should be in feet, something like that. But if you use this equation, you can see that this equation, there are constants 20.9 and 87. And it specifically, told you what units you should use for wing loading, pound per feet square.
Yes, sir.
So to use this equation, the wing loading should be in pound per feet square. Everything else is just non-dimensional numbers. They don't depend on units. Since it's empirical, this TOP estimation should be done only with this units. Only then this equation is valid. Otherwise, the constant will change if you use some other units for the wing loading. Clear?
Yes, I got it.
Yeah. So now using this, now what you have, you fix your STO, you have a relationship between T by W and W by S. So you take all T by W to one side, W by S to another side. Express T by W as a function of wing loading. It's possible to do that. You got it?
Yes, sir. Yes, sir.
Now you plot I will appreciate it if you can, do the wing loading in meter per wing, Newton per meter squared. But if you want to be consistent, it's up to you. After doing the calculation, you convert everything to this unit and plot. I will appreciate that. Okay.
Okay, sir.
While plotting, you do in SI. Now, if you plot another one for no, just takeoff is say 400 meter, then you don't want that, correct? You don't want to be in that region. You want it to be 300 meter. If just takeoff is 400 meter, that means it's a wrong area. So you want, suppose you plot for 500 meters here. Sorry, 200 meters. The curve may be shifting. For various values, let's take off. I am plotting. You got it now?
Yes, sir.
Right.
So
Yeah.
for different takeoff value, we'll get
Length. Yeah.
the takeoff length.
So whatever, suppose 300 meter is your length. I'm marking it as red because that is specified in a specification. I can't compromise too much on that. That's what it means to me. Okay. So my
Yes, sir.
feasible region will be only in this direction. Whatever is below is not feasible. Okay. So don't show the feasible region and just for your just plot so much and leave it. Okay.
Okay, sir.
Plot this much and leave it. Your takeoff, your STO graph is over with this. Okay.
Yes, sir.
It may not look like this. Graph may look like what you told, something like this also. Okay.
Yeah, yeah.
Don't worry. Just mark what is your length so that we'll know which is a feasible area and which is a non-feasible area. Got it?
Yes, I got it, sir.
Now the most important thing is this one. The red line is more important for superimposing with other constraints.
Okay, sir.
Yes. Now you can go to the next one. This is what I want for. Similarly, or you can once if you fix your STO, okay. Say your STO is fixed, but you want to vary the CL max. You are not getting proper thing later or something. Huh? So you quickly want to see whether increasing CL max will help. You see what I'm telling? Later on, you may discover that okay, I want this is a feasible region, but I may want to move it up or down. You got it? Because it is probably restricting my feasible region. So for that, be prepared now itself. All I'm asking is take a STO is equal to sorry, I'm already telling. So STO, you just take it as 300 meters. What is given in the book? Okay. What is given in the specification?
Yes, sir.
Then you plot another graph, which is here. For all these graphs, STO is 300 meters, but you vary CL max. Okay.
Yes, sir.
This is CL max is 1.2. Probably CL max is 1. Then CL max is 1.3, etc. This may be of use later. Just plot it and keep it. May or may not be of use, but I want you to plot this.
Okay, sir. We'll plot it.
Okay. So this is one. Then it's over. Okay. Then wing loading effect on landing. If you look at this, for what have you done? You show me.
Yes, sir. I'll show. Is my screen visible?
Yeah.
So, this is the same way that we plotted
Uh,
the way that you have just said, P by W versus W by S. The only thing we did was we took the platform area, we assumed platform area directly, and we didn't
no, don't do
consider.
that. Don't do
Yes,
that. Because
yes,
platform area should be the output of the wing loading.
yes,
If
exactly.
you assume it earlier on, then the whole purpose is lost.
Yes, sir. So we
Okay.
have to take the required constraint of airport length.
No, don't do that. See, you again use this book. Do you have another expression for landing? What I'm telling is, now I'll share my screen. Huh? I'm going to share my screen now.
Okay, sir.
Are you able to see my screen?
Yes, sir.
You have LP is W by S into 1 by sigma CL max. Correct? Here again, W by S should be in pound per feet square to use this relationship. LP is landing parameter. Okay.
Yes,
Then
sir.
SL will be in feet. Here also, earlier also, the landing S takeoff should be in feet to use that expression. Okay.
Okay, sir.
Don't forget to convert everything to consistent units. Then you get a wrong answer. But if you look at this, it's just for illustration. Okay, how to draw it. So don't. I won't bother if you don't get the exact correct answer. That is not the issue here. Okay. But I want you to draw all these graphs and see how they look like.
Yes,
Understand,
sir.
right? Yeah. So this landing parameter is being loading into 1 by sigma CL max. Now, here also you use this 3.6 and 3.7 equation. What you see is there is no T by W in this equation, only wing loading. Correct?
Yes,
Not,
sir. Yes, sir. T by W is not there.
not there. So, how will it look like in this graph? And bother only with the same graph now.
Yes, sir.
It will just look like a straight line. So, how do you get that? Wing loading you assume as unknown and substitute in this equation 3.7. You can get the wing loading. Correct?
But sir, T by W isn't there, sir.
Isn't there? So, just draw one straight line for wing loading. What you will get? This is the wing loading. Straight. Whatever. Are you hearing me?
Yes, sir. Audible, sir.
Yeah. So, whatever be the T by W, there is only one wing loading. Are you getting it?
Okay,
For
sir.
landing. This is W by S for landing. Okay.
Yes, sir.
What is this based on?
Max,
Look at those expressions.
real max, sir.
Landing length and
Landing
CL
line,
max.
real max.
CL max. CL max. These are the things. So plot these for various landing lengths. For example, this will be SL is equal to say 300 meters. If you decrease SL, okay, probably look at this expression. What does it say? If you decrease wing loading, landing parameter will decrease. Okay, or you fix that wing loading instead of say you whatever you want. Okay, and you play with CL max now. For various CL max, you draw this figure. You don't have to put red or this right now. Later, CL max is equal to 1. When you increase CL max, okay? When you increase CL max, what will happen? Look at the equation. The landing wing loading will be actually, you find out, okay, whether CL max come to the right or left of this. You can easily find it. Probably this is SL is for CL max is equal to 0.8. This is for CL max is equal to 1.2. Right now, you don't put, either feasible or infeasible. You calculate this and keep it. Later, you can put it as a constraint with the suitable CL max. Okay. You understand what to do in this?
Yes, sir.
Yeah. Okay. Now, what is the next one? Show me a presentation now.
Climb.
Landing only do this. Okay, nothing else. Then climb. Yeah, go to climb.
Yes, sir.
Sure.
Cruise and so.
Yeah, what have you done first? Climb first, cruise later. Okay.
Yes, sir.
Go according to your mission profile.
Yes, sir. Sir, we assume the rate of climb from the table.
What is it? Yours is what type of aircraft?
Regional short haul aircraft.
Right. So, does it have passengers inside?
Yes, sir.
Yeah. So, don't take that. Take FAR Part 25, commercial.
25, sir.
Or,
Okay.
Okay. Just because there are people inside, in case engine fails, you want to have protection for them. So, you have more than one engine. Let's say 2 engines.
Yes, sir.
You have 2 conditions here. One engine inoperative, gear up, one engine inoperative. Okay.
Yes, sir.
And gear down, one engine inoperative. You assume if you have 5 engines, assume one of them fails. If you have 4 engines, assume one of them fails. If you have 2 engines, assume one of them fails. One engine inoperative. So you should have at least 2 engines per aircraft.
Yes, sir.
And you satisfy those conditions.
Okay, sir.
What are those conditions? 3% at V climb. How do you know V climb? You assume the V stall from comparison aircraft.
Reference aircraft.
Comparison aircraft, yeah. Then multiply with 1.2, you will get V climb. 1.1 or 1.2. Okay, you can refer your earlier 1.2 you did. Yeah, 1.2 you
Okay,
You can
sir.
get this idea from flight mechanics literature. Should be 1.2 or 1.1. Okay.
Yes, sir. Sir, but how will we get the G value, sir?
G is 3%, 0.03 given to you.
0.3%.
3% is 0.03.
Okay. 3%.
Then next one is 0.005. That is G value.
Okay.
Okay.
So after making the appropriate substitution, we'll
Yes.
get. Okay.
Now CD naught by 4 pi AE is nothing but what is it? You assume these values, aspect ratio, everything you may have to assume here.
Yes, sir. Aspect
From
ratio.
comparison aspect.
Yes, sir.
CD naught.
Sir,
etc.
sorry for the interruption. Sir,
Yeah.
G value over here, sir, it is climb factor, I think, sir. It is not the gear up for one engine in operative thing.
So I think this is rate of climb by the climb velocity.
Yes, that is G.
Okay, sir. So that should be assumed as 3% of V climb, sir.
Yes, so G will be 0.03.
Okay.
Correct? You understand?
Yes, sir.
Time
Understood.
velocity by V. No, I am asking Sanjay whether he understood.
No, sir. I didn't get,
No.
sir. Sir, what in the book they have said is G is a climb factor. So that is rate of climb by climb velocity.
Yeah. So
So,
what
sir,
he's
like
telling,
rate of
what?
climb we have assumed based on our historical aircraft data,
No,
and
no,
we
don't do that.
climb
Don't do
this.
that. Don't do that. Don't do that. Right. For this, see, that is your own specification. So you have to do three things. These people don't have a climb specification. Okay.
Okay.
For you, you will have climb specifications. Then you have to plot this one and your specification also. Okay. You have to plot everything and take the worst case.
Okay.
Okay. This here, this design doesn't. They don't have any climb specification given to them. So they rely only on the FAR specification.
Okay.
For you, you should yours is military. You may have to, either satisfy the first one or two. Yours military or what? Yeah.
Yes, sir.
You
Maritime.
have so you have to, if it is given to you, see whether that is worse than this. What is given here, or you
Okay.
plot all three and see
Actually,
which
it is
one is the
not
worst.
given, sir.
Huh?
It's not given, sir.
It's not given for you.
No, sir.
Then if it is very important for your aircraft, you have to look at the at least this should be these two should be specified to military mil specification MILC 5011A.
Okay.
For them, they have to make sure they are part 25 is satisfied.
Okay.
Okay.
Thank
Yeah.
you, sir.
Thank you. You can share, Raj. Yeah, you are sharing. Yes.
So,
Now you substitute that G here. You get a
okay.
relationship between T by W and W by S.
Yes, sir.
So for every T by W, you calculate W by S.
Okay.
Or every
Yeah.
W by S, or you assume W by S, you get two values of T by W. So your curve, actually, you are showing only a part of the curve.
So we would be again plotting the graph. So.
Huh? Yeah, same graph. Okay.
Okay.
So what will you, how will it look? Usually it will look like this. Okay. For you, it is looking something like this. Okay. We'll go for the slightly start line. Okay. It will look like this. This is yours. Okay. Raj.
Yes, sir.
Yeah. So now you plot this for various values of climb. Maybe this is 3%. Okay. Maybe this is 0.05%. For 4%, it may be probably like this. I'm not sure. Okay. So you'll know that if it's 4%, it is acceptable. If it is less than this, it's not acceptable. So feasible region is only down. Or if it is the other way, feasible region is only up. You come to such conclusion. Okay, Raj?
Yes, sir. So what is difference between part 23 and part 25?
See, in part 23, gear up, all engines operative. Look at the leftmost this one. You
Yes,
bother
sir.
only about all engines operative without the landing gear.
Okay.
That is, the gear is inside, it is retracted. So at
Yes, sir.
sea level, it should have a climb rate of 300 feet per minute minimum. That is part 23 for civil. Cargo aircrafts may be using it. Agricultural aircraft may be using it. When you say commercial, probably there is human life involved.
Okay, sir.
So for that you use the right sign. What is the difference? Here, the 300 feet per minute is not given. Climb rate is not. They don't bother about it, but they are bothered about the gradient of climb.
Gradient.
And also look at left hand side. They are not bothered about all engines operative. Okay. With one engine inoperative itself, gear up with landing gear retracted, it should be 3% gradient. Then, if landing gear is down, which means that CD naught is increased. You got the catch now?
Okay.
Same, one engine operative means suppose you have two engines. One engine operative means you will be using only T by 2 into W here. Instead of T, you will be using T by W in this equation. Sorry, T by 2 in this equation.
Okay.
If you have three engines, you will be using only 2/3 of T in this equation.
Yes, sir.
And you have CD naught for OEI with gear up. What the gear down means CD naught will increase in this equation. Still with OEI, one engine operator.
One engine operator.
You got the differences now?
Yes, sir.
Yeah. Okay, the whole class, it's for the whole class, okay? Whole class, any doubts? Right, only if you do, you'll get this clarity. If I taught the same thing in class, but you won't get it, right? That's why,
Okay.
the exercise is important. What
Yes,
you
sir.
do is important.
Yes, sir.
Sir, I have another question.
Yeah, tell me.
Yeah, sir, in the denominator we have Q. So in the Q is half rho V square. So the rho is rho airport, right, sir?
See, these two, there's no confusion for military and civil. At sea level, it's given.
Yes. Yes, sir.
But for the commercial one, it is airport height.
Okay. Okay, sir.
Good question, but I thought I will, leave it out for you to figure out. Yeah. Okay. Never mind. Sorry.
Okay.
He was doing it today, so I got this out.
Okay. Okay.
Thanks.
Yeah. Tell Raj. So for you, Raj,
Yes,
commercial
sir.
should have at the airport height, rho, the sigma and everything.
Yes, sir.
Should be careful there. Look at each and every term and question the what you should use for that.
Okay, sir.
You won't make mistakes.
And this was for the cruise, sir.
Wait. Oh yeah. So the cruise.
So the
Cruising
cruising
mark.
altitude.
Okay, so assume CD naught. Use the same CD naught and K for all your wing loading.
Yes, sir. We'll use the same for other calculations also.
Yeah. Okay. Where did you
And
get it from? From comparison aircraft, correct?
yes, sir. Reference icon.
Okay. Right.
And
So with this wing loading cruise again, you plot like this.
the
And I
same.
share my screen. Huh? Just
Okay.
like landing, no? Just like landing.
Okay, sir.
What you do is here the main parameter is V cruise, correct?
Yes, sir.
So should I share my screen?
Yes, sir.
Okay. Acceleration you don't have, so I won't explain right now. If someone has the acceleration problem, I'll come to it in the part. So the range is actually cruise. Okay. Now he has given CD naught by 2K. Why? Root of CD naught by K is actually your optimum CL, correct?
Yes, sir.
Dividing by 1 by root 2. So that to give an allowance, you may not be flying at L by D max during cruise. At 0.94 L by D max is there, no? You'll be flying there at that point. You're assuming even worse. 1 by root 2 times that. Only, telling, it's it's slightly less than that. Okay. The sail you're flying, just he's estimating it. You can also use the CL there. You can assume the CL cruise.
We are not sharing your screen, sir.
Oh, I made the same mistake. It's shared now.
Yes, sir. Visible.
Yes, sir.
So now you have wing loading effect on range. This is actually the cruise. Okay. Right.
Yes, sir.
Look at 3.21. Wing loading at cruise is Q into CL. Very simple. That will also be a straight line, just like landing. See, just like landing. That's also going to be a straight line. It may be like this. Okay.
For the cruise.
Wing loading cruise. Now you do two things here also. When you plot it for different velocities. For a higher velocity, you get a higher wing loading or lower wing loading. Q is here, so you get a higher wing loading.
Higher wing load.
Yeah.
Directly.
So this may be a higher velocity, which is okay. So anywhere toward the right is feasible. So the left is not feasible. Okay.
Okay, sir.
So you can just plot for a few velocities more than this and less than this, and show the feasible region. And plot another T by W versus, just like we have two graphs here also. Wing loading. For the same thing, for the same wing loading, that is this one. Very CL. Okay. CL is root of CD naught by K is the best. I mean, probably the optimum you want. What if increase CL and decrease CL? What's happened? Plot here from that figure. Okay.
So in the second graph, we'll be wearing CL, sir.
Yeah. But just for the heck of it, only the first graph is very important. Second is only if you run into trouble, you can use the second graph. If you run into trouble, all these graphs will help you later. Some of them I asked you to plot because in case you run into trouble, you don't have to plot at that point of time. You can plot right now.
Yes, sir.
Preparing for the, any problem later.
Yes, sir.
Yes, now cruise is over. Then combat you don't have.
No, sir, we don't have combat.
Turn rate you don't have.
No,
Sustained
sir.
turn rate, all part of combat.
Yes, sir.
You don't have acceleration. Flight ceiling. Did I give you a flight ceiling condition for you?
No, it wasn't.
It wasn't given, but you assumed a ceiling. Okay.
Okay, sir.
So now what you do is, this is also like that, but CL will be different here. Q will be different, CL will be different for flight ceiling. Do the same thing.
The same graph.
Because Q, the flight ceiling height, rho will be different, density will be different, correct?
Yes, sir.
Now, depending on CL value, your wing loading is going to change at ceiling. Okay.
Yes, sir. We'll be wearing CL, no, sir.
Yeah. You can vary CL. You can vary you can keep, actually you can assume the ceiling velocity to be a cruise velocity. Okay. It will be slightly more than that actually. And CL you can decrease a little bit. The density will be less at ceiling, no?
Yes, sir. So we should assume ceiling velocity as the cruise velocity, sir.
No. The ceiling velocity is slightly more than your cruise velocity. Because if you look at the flight, this one, no? You remember your flight mechanics. You look at this graph. Let's say this is altitude, h. This is velocity. The flight envelope will look like this, correct? So your cruise velocity will be here, maybe here, or here. Which one will you choose? Here. Ceiling velocity can have only one velocity. So you can have a lower velocity also. Yeah.
Okay.
But then at ceiling, the CL will be different. At this stage, you don't know what CL to take. Okay.
Yes, sir.
And rho is fixed, but rho is known. because you fix your ceiling.
Height is known. No.
Yeah. So now you fix your ceiling and then again plot the same graph for various values of CL and for various values of V. Same way, we can choose some, you fix the value of V and vary CL.
Okay, sir.
Whereas the other one, you fix the value of CL and vary V. Both things you have. If you want to have a different one, it will help you. This comparison of these two will help you. And denote the feasible and infeasible regions in this graph also. But not here. It will be T by W as a W by S. It will look like you're landing on it.
Okay, sir.
It will be a straight line. So you may say, no, this is feasible, this is not feasible. Okay. Now, don't assume rho. Okay. The trick here is rho will tell you whether your ceiling height is attained or not. Correct?
Yes.
In this equation. So you have to find rho from this equation. So rho as a function of wing loading, what is it? CL and velocity is given here. You find out for, yeah, you can do that way also. For what value of wing loading will we get that rho? So if wing loading is more than that, what will happen? If wing loading is less than that, my ceiling will decrease. Wing loading is more than that, ceiling will increase. Like that you can reason out from this. Half rho v squared. If wing loading increases, rho will increase, correct? Which you don't want. Rho should increase, keeping other two constant. Keep CL constant, V constant. Okay? Raj.
Yes, sir. Yes, sir.
So this equation says that you should bring down the wing loading so that you can reach the ceiling. That's what this equation says. If you want to change that, fiddle with your velocity and CL.
Okay, sir.
But this is something which you brought on your own head. Okay? I never gave this ceiling to you.
Yes, sir.
So
Wasn't
such things you mark with say green, which means if you want to change it later, you can change. So for example, I'll put a green line here, which means this is what I have assumed to be the ceiling. This is the graph for that. Okay?
Yes, sir. So that's like we can modify it in the future.
Later, future. Yeah, if it is giving you some infeasible reason, you can move it to the right or left and try to do something. Okay.
Sir. Yes, sir. Got it.
Then glide rate you don't have.
No, sir, we don't.
Okay. So
Yes, sir,
that's it.
That's
That's it.
fine.
If you now after doing all this, the last step. Be the red lines are there, no? What is given a specification? What is given? A takeoff.
Constraints, sir.
Yeah, takeoff is something like this, let's say. And let's say top is feasible or bottom is feasible for your whatever you have seen.
Top is visible, sir.
So let's say bottom we don't have anything. So I just I just put a small arrow to know that this is a feasible region. Okay.
Yes, sir.
And then what else you have for climber? After takeoff, climb.
Yes, sir.
Climb, you say you have. That's also given to you by me or it is given by FAR specification, correct?
Yeah, FAR.
You have two such curves. 3% maybe like this. So probably only this area is feasible. I'm putting in an orange color, you see, or yellow
Yes,
color.
sir. Yeah. Yes, sir.
Then this is 0.5%, 0.05% maybe here. For other groups, it may be different. For you, it is point. This is 3%.
0.
This may be also here. So the worst case is this one. In this case, it may not be like this. It may cut the curve something like this also.
Okay.
Because CD naught is different, correct?
Yes, sir.
So in this case, combining all these two, you'll say, as far as this graph is concerned, only this is a feasible region. Okay. Here.
The
Here,
intersection.
yeah. Then what else do you have? Landing, correct?
Yes, sir. Landing.
Oh, cruise is there. So for cruise, I'm again, did I give the input? Yes. So put it in red color. Wing loading, more than that is feasible. Less than that is not feasible. Okay.
Yes, sir.
Then landing, also I gave. So let's say,
The ceiling.
Hmm?
Ceiling.
Ceiling, you brought it on yourself. So put it in green. For ceiling, suppose you get this. Okay. So the right is feasible. To the left is not feasible. You are getting. I'm putting an arrow like this. Then for landing, probably I'm putting in red what I gave. I'm getting something here. So the left is feasible, right is not feasible, just for the heck of it. Okay.
Okay, sir.
So now where is a feasible region? Should be above this, above this, above this, above this, to the right of this, to the right of this, to the left of this.
Yes,
So
sir.
the feasible region you can say is only here. Correct?
Yes, sir. That's
In your
correct.
case, all these lines may interplay with them in various manners for various designs. It won't be the same for all of you. Now,
Okay.
this green is not creating a problem for you now. Now, green is somewhere here. Then only right is feasible. Then you have to bring down the green to somewhere here by varying some parameters. Okay. So
Yes,
you can
sir.
vary this green ones. Okay.
Okay, sir.
So that's it. This is the final graph I want. And from
Finally,
this, finally, you have to choose. You have wing loading. You have to select. No.
yes, sir.
Out of this, I am choosing one which will have the smallest T by W because I spend the less power on engine. Ideally, this should be my wing loading. But
Wing
I'm
loading.
for yeah, that should be, but I'm taking it some range. Okay, from here to say here. Okay, take this as a wing loading or somewhere here in the feasible region, very near this point.
Yes, sir.
The lowest possible T by W. Sometimes the highest possible wing loading may also be a boom. So I may take this also. It depends on your specific. You look at your, you think deeply about the function of your aircraft and decide where you should take. I want to
Okay.
minimize the thrust, no? So it should be near this bottom.
Yes.
Wing loading, you want to minimize or maximize. You look at your requirements and decide.
Yes, sir. So finally, in the report, we have to.
Wait. So finally, I should put. I don't want T by W now. This is only for this one. I want what wing loading I have selected. I'll say wing loading is 1250 Newton per meter square. This is what I want. At this point, what is the wing load? Where I selected maybe 1250. This point. Okay.
Yes, sir. From the graph.
So I'm getting. I want this number as output of this exercise. After going through all this.
Okay, sir.
You don't have to compare this with your comparison aircraft right now. Okay.
Yes, sir.
Yeah. Just
Yes,
do this. That's all. Clear?
yes, sir. Yes, I got it, sir.
Okay. So tomorrow, who will make the presentation? Military transport. Who's making it?
Sir, it's roll number 11, sir.
Roll number 11. Who is that?
CB.
CB.
Yes, sir.
Okay. So thank you. I'll take attendance. Raj, you made a good effort. Can you show me all your slides?
Yes, sir. I'll show you.
Yeah. Ramanathan has a question. We'll just answer the question shortly.
The screen visible?
Yeah.
Mission profile.
Hmm. Yeah. Next one. Next.
Yes, sir. The graph.
Yeah. Okay. I understood what you did. Go to. Yeah, next one.
Yes, sir.
Hmm. Hmm. Yes. Okay. Okay.
Yes, sir.
So Sandita should collect all the weight estimation reports and load them.
Sir, we
Not,
have mailed you the weight estimation.
sorry, weight estimation.
PPTs.
PPTs.
Yes.
Sandita is here. Yeah.
Sir, I'm
she's
here.
So they will send all the weight estimation PPTs. You make
Sir,
another folder, weight estimation in that MS Teams, and then you upload them there.
okay.
Okay. Better not use MS
Sir,
Teams. We have,
sir, should I start collecting the wing loading as well, or
No. Only weight estimation. That
okay,
wing loading is presentations complete. After that,
okay, sir.
so thanks to the
Sir.
Raj.
Yes,
Wait,
sir.
Ramnath, I'll come to you. Okay. Yes. Now, thank you, Raj. Any
Thank you, sir.
questions? Thank you. Any questions from Ramnath? I will answer. If Raj cannot answer. Yeah.
Sir,
Ramnath.
even for our case, you didn't mention any ceilings. So, but you have given cruising altitude to be 30 kilometers. So, will I take some 10% or something more?
What is your type of aircraft?
Solar stations.
You take it from comparison aircraft. Even though I haven't given you, it should look reasonable.
Okay, sir.
So
Sir,
you give it as a green one. Huh? If you
okay,
want,
sir.
you can fiddle a little bit here and there. Because I haven't given you that. Okay. Yeah.
Yes, sir. Sir, and for this takeoff and landing, sir, shall I assume, means I thought of taking a case as Tiruchirappalli Airport, sir, because it has the shortest schedule. But,
No, see, for solar and you take off and landing
yes, sir.
is a spy plane, no?
Yes, sir.
So it should be very short takeoff and landing from anywhere near the border.
Near the
Okay. Yes. Now Rajeshri has a question.
Sir, you were showing a plot for of wing load thrust to weight ratio versus
Yeah.
wing loading,
Yeah.
and for cruise, right? And you
Hmm.
said we have to vary the cruise velocity and see how that varies. Since
Yeah,
we
that's
have
just to find the feasible region. Your cruise velocity should be more than at least more than what is given to you. If you cannot achieve that velocity, then you are failing short of the requirement. So to determine that, you vary the velocity and see which side is feasible.
okay. So if we find out that it's possible, then we have to change the whole weight estimation also.
No need. Don't go back right this point of time. There may be some time in future when you may have to go back, not right now. It is okay to have a wrong weight first, then you have a different thing here. Then next one also something may change. It is okay at this point of time. Only next cycle of conceptual design you'll get a better idea. You're doing only one cycle here. You will do a refined weight estimation at a later point of time, so don't worry.
Sir, and also now that we're varying the velocity, so can we keep the altitude the same
Yes, yes.
and then change it? So we'll
Yes, one
change
is
the north
changed.
pole.
Yes, exactly, exactly. Yes, that's
Okay.
how you should do it. Yes,
Okay.
Krishna has a
Thank you.
question.
Yes, sir. You hadn't specified any cruising altitude for us, nor had you given us a service ceiling. So we assumed a service ceiling of 5,000 meters above sea level.
Well, I haven't given a service ceiling also.
No, sir.
Yeah. You again, you take it from reference aircrafts. Okay.
So the cruising altitude?
If I have not given, you can suitably assume.
Okay, sir. Thank you.
Suitably assume, because that's why you have the reference aircrafts for.
Yes, sir.
See, the person who wants to do, who's putting the money, may not be a technical person. He may be a business person. Okay.
Okay,
So
sir.
he will just say what will give him profit. And as a technical person, we have to tell, see, this is what you'll get. Okay. In addition, I'm giving you this also.
Okay, sir.
Now, he may say, in addition, if you don't want that, I want something else. That will come later. But be prepared for that now. So you vary all these things and see. To show him, you show him, you go to the right, it's possible. If you go to the left, it's not possible. You'll get less cruise velocity.
Okay, sir. Thank you, sir.
Later on, he may say, you gave me this option, no? I don't want that. I want to fix it here. He may put his finger on some number and say, I want this. So be prepared for all that. He make these graphs ready.
Okay, sir. Thank you, sir.
Not that you may be using all of that, but you should know how to do all of that. That is the point of this exercise. You understand?
Yes, sir.
Yeah. So get trained. The training is the important thing now in this course. You look at others also. So what you missed out, you get from others.
Okay, sir.
Okay. Thank you. Any other questions? What class do you have next hour?
Sir, we have a technical training from CIR.
Okay. All the best.